This is this is lecture 8, called Particle and Central Potential. It's part of a mathematical physics course on quantum mechanics at senior level. The first author of the text using for this course is Davies. Here's the text. Quantum Mechanics. It's the second edition. Two authors, Davies and Betts. I do this every chapter. Two comments before I start into the nitty-gritty, the details. I mentioned a bit earlier session, not too far back, I was wondering about the influence of the two texts that I'll be using. Now, the one by Davies is the one using at the moment. And now the next quantum mechanical course will be at M1 level, using this text. And looking at the two of them, I would say that one of them was strongly influenced by the other. So I was curious to know which one came first, which one got written first. So the obvious thing to do is just check the dates, the publication dates of the two texts. And I found that the M1 level course by Mandel, it was published in '92. And the Davies book, but this is the second edition. So I looked at the first edition, and assuming he didn't radically change it between the first and the second, so the first edition was published in '84. So my hypothesis is, my suspicion is, that Mandel was strongly influenced by Davies. Now that is a plus and a minus, an advantage and a disadvantage. It means that there will be a little bit, well, some overlap between the two texts, and that's the plus in the sense that a lot of the some of the material in this book, the M1 book, will be familiar to you from the senior level course you're doing at the moment. The disadvantage, of course, is you might find it a little bit repetitive, some of it, but reinforcement's not a bad thing. It's part of learning. But there's plenty of new stuff. That's why it's an M1 level course. One of the attractions of this book is we'll discuss the famous Bell inequality, concerned with non-locality or entanglement, which I consider, and a lot of physicists consider, the weirdest phenomenon in physics. Right. Now the other comment I wanted to make was the last sessions of, the last session of the theory part of chapter 7 was pretty much in the dark. So I never know how things are going to turn out until I actually look at the result. So I was experimenting. I've moved back into the living room, and to solve the lights too bright, there were 3 light bulbs in the light where I'm pointing in the ceiling, and they were hurting my eyes. It was just too bright. So I took out 2, leaving 1. And as I got to the 4th session of the board, the daylight had gone, and even now it's 5:20 p.m. and the light is starting to fade. I'm going to have to change my routine somewhat, or get into a routine that works, in the sense, I get all the preparatory work, get all the board written up in time enough for me to film while there's still daylight. And it's a good thing to have daylight on the board, because I notice the visibility of the text on the board is a lot better. So the last session of the previous chapter 7, was pretty disastrous. So that motivated me, as far as possible, to try to lecture during the daylight, during daytime. Now there are other ideas. one is to put one more light bulb back into the light, so increase the lighting, and then so that I can film at night. Another idea is, now the lighting is fixed, but I could shift the board. I can put in another screw. With this large whiteboard, I need 3 screws for support that are screwed into the wood of my bookcases. I have wooden bookcases. So I could put in another screw to the left of this edge, and I can shift the board up so that the lighting is closer to the square 7 and 8 of the board corresponding to the 4th session, which tends to be filmed later, so it may get darker. But probably, well, it's still, even well into the 2nd course, still experimenting, still trying stuff. Have not yet settled into a fixed routine that really works, with proven experience. Haven't got there yet, which is sort of annoying. One idea I'll try is just to get going on writing this up earlier in the day, so that I don't run out of daylight. Because as you can imagine, it takes hours to write up all this stuff, and then I have to read it to be able to present it to you well enough. And that's part of the plan, of course. This stuff's undergrad, but when this stuff starts getting really hard, the whole point of the exercise, well, 2 main reasons I make these videos. One is it's a fantastic motivator for self-study. Right? So I want to really master the higher level stuff, and so teaching it is a means, right? It's a stepping stone. So that's the purely selfish motivation. And of course, there's the other one. And that is providing free graduate level education in math and physics. That's very important, and I'm hoping in time the planet will wake up to the significance of what I'm trying to do. I hope other people, especially retired professors, will be inspired and do the same thing, and then give their knowledge before they die, and then all their knowledge is just lost, wasted. What a waste. They can give that to humanity, and then hundreds of millions of parents can then be freed up from the great expense of paying for their children's higher education, when it could be done for free. So it's significant in that sense. So I have a string of motivations for doing this stuff. All right. Okay. So a new chapter, a new topic. I suppose the features of this chapter, we will examine in greater depth the radial part of the Schrödinger equation. The part of the wave function that's concerned is a function of position, r, the position vector. But this time taking more into account the angular momentum, as you'll see in the next few sessions. Because now we've done angular momentum. That was the previous chapter, chapter 7. Now this is chapter 8. Now, the quantum mechanical problem of analyzing the behavior of quantum systems, where you have a central potential. I mean, if you think about it, like an atom, right? An atom is vastly empty space. There's hardly anything there, right? And the electrons, if you increase the size of an atom to, say, the size of a cathedral, then the nucleus would be the size of a fly, just an ordinary house fly. So it gives you an idea. So the fly is of the order of 100,000 times smaller than the cathedral, and the nucleus is about 100,000 times smaller than the atom, which is pretty amazing. So the atom is mostly empty space. So and yet most of the mass resides in the nucleus. and that's where all the protons are. So it's a highly localized source of charge. There's a lot of charge there, and that charge, you know, on the protons, the positive charge on the protons, that generates a potential you know, around the nucleus that the electrons feel. So if you differentiate the potential, you get the force, well, not times the charge. You have to multiply by the charge, of course. The force will increase if there's more charge in the electron. Depends on the charge on the electron. So anyway, that nucleus generates a potential, right? It's centrally located. So the potential, its value, will just depend on the distance to the nucleus from that point. So it's a central potential. Okay? Now, because atoms are so important to quantum mechanics, this problem of examining the behavior of central potentials is very important, okay, for quantum mechanics. Central potential tends to be spherically symmetric. The potential will be spherically symmetric. The polar angles don't really matter much. Now that leads to a bit of a paradox that I'll talk about in a couple of sessions. It seems like a paradox, but it's not. You can resolve it. But so we will now bring in the angular momentum type factors in our Schrodinger equation. You may remember quite a few chapters back, we had a sort of mysterious L times L plus 1 term in the Schrodinger equation, and it was a bit mysterious, didn't know where it came from. Well, now we know. I mean, you know, this session and well, the next, you'll understand where it comes from. Well, now that we've done the chapter on angular momentum, you'll follow it. So this chapter will add the angular momentum terms in the Schrodinger equation. But even so, we'll still concentrate on the radial part of the Schrodinger equation. The psi function, we can still split, to simplify things, so we can still split it into a radial, you know, an R factor, and the polar angles factor. So the wave function splits into two functions. One's a function of R, the position, and